shortly. This is a two-hour session, and which is make up for the Monday class that we missed. So let me share. You let me know whether there is something visible on your side. Okay, so yeah, I was just informed that you are waiting for the link so as to join the class. Just to clarify that for all our online sessions, we'll be using the link that was shared, the very first time we had this online class, or the link that has been shared today. So anytime we have an online session, we are using the same link. And for the notes that we'll be taking in this online session, I will be sharing them on the classroom platform. So I believe once I post them there, you should get a notification on your side. So I hope that is clear.
Yes, it's noted. I will communicate to the class.
Okay. So yeah, maybe to contextualize what we are covering today, from our course outline, the first thing that we were to look at is the semiconductor memories. And under this, uh, amongst uh, amongst other things, we were to look at the classification. And characteristics of memories. Um, there are still people waiting to be admitted in. Okay, can continue. So a classification and characteristics of memories. And here we were to look at the read only memories, also the random access memories. And currently that is where we are, where we yesterday we were looking at the static random access memory, and we also commenced on the dynamic RAM access memory, the DRAM. Um, Once we are done with that, we'll also be looking at expansion of memory. And then we'll be looking at the programmable logic. But as I said yesterday, our online sessions will be trying to cover on this, the programmable logic, because it is the most appropriate platform to cover this. So maybe 2 sessions thereabout, 2 hour sessions. We'll need to be able to cover that area starting today. So I just brought up this so that you are not confused as to how today's class connects with yesterday's session. So we'll still be covering the DRAM in our physical class. We'll finish on that and progress as shown here. But for our online sessions, we'll be looking at these the programmable logic. So that is what we'll be covering today, and I hope that puts into context our session. Okay, so programmable logic devices. That is PLDs. So what are programmable logic devices? I hope this is the last person I need to admit. So what are programmable logic devices? Also to to contextualize this within the digital systems or digital electronics field, we'll have a family tree of the various devices and technologies, which will give us a better idea of where programmable logic devices fall. So I'll very quickly put that up, within the digital ecosystem. So within the digital ecosystem, we have, I would say 3 major families of components or systems, and at least one or maybe even the 3 of them we are familiar with one way or another. So one family of digital systems is the standard logic. The standard logic, and this is what we were actually reviewing even yesterday. So under the standard logic, we find technologies such as can somebody raise their hand? Alphonse Omolo?
Excuse me, sir. There's just a lot of
Yes, Alphonse, your hand is up. Or,
there's a lot of background noise.
sorry, I cannot hear you. Am I audible?
Yes.
Okay. Then probably that was a mistake on his side. So standard logic, I was asking which technologies do we find here? We reviewed this yesterday. There is a lot of background noise. Okay. Well, I suspect it is my machine, which has really kind of seen better days, and it's a bit noisy. Let me see. Okay. So is it better now?
Yes.
Okay. Thanks. So let us continue. And I will not be able to check on the the meeting side because I only have this Word document in my display. So if I ask for a response, kindly just unmute and say something, because I'll not be able to see any raised hands or comments. So I was asking on this standard logic, and I was saying we had reviewed them yesterday. Can somebody give me at least one?
CMOS.
Yes, Simo. So yesterday we actually looked very briefly on this. So we have the TTL logic, we have the CMOS, and the CMOS, of course, is based on the metal oxide semiconductor technology, the MOS, that is PMOS and the NMOS, and we also have the emitter coupled logic. So these are the three main standard logic technologies. So apart from the standard logic, we have the ASICs, that is the application specific integrated circuits. And maybe before we go on to what is under the ASICs, the other digital system kind of family are the microprocessors and the digital signal processors. So we have microprocessors and the DSPs. So you'll find that most of the chips or the components in digital systems, they will fall under these three main categories. So what we find under the ASICs, the application specific integrated circuits. So examples of what we'll find here is the programmable logic devices, the PLDs, programmable logic devices. Then we have the gate arrays. We have, I think somebody wanted to join. Oh, okay, there's nobody. We can continue. So gate arrays. Also have cell-based. We have cell-based ASICs and full custom full custom application specific ICs. So when we talk of, for example, the full custom, this is whereby the will I say the manufacturer, or the owner of that particular chip actually does all the designs from scratch. So they will be having their own transistors designed and laid out in the silicon wafer and so forth, all the way to from scratch all the way to having the final product. And I believe, for example, I'm not sure, but it's up for confirmation. When we talk of the Apple processors, I don't know where now they are in which M series. I think there was M1, maybe M3, I'm not sure. And those are among the fastest processors we have out there. Some of them having, I think, more than, I don't know the number of transistors offered, but it is in their billions, probably more than 100, actually more than 100 billion transistors in those chips. And I do believe that they design everything from scratch, and as such, that is would be an example of a full custom ASIC. Then I think our interest or in this tree diagram is these programmable logic devices, where they fall, and we can see that indeed they are under the application specific integrated circuits. So that is what will be kind of categorizing even further. The rest they have the other categories, semi categories and so forth, but our interest is on the PLDs. So that is what we'll categorize a little bit further. So under the programmable logic devices, we have two main PLDs categories. We have the combinational PLDs, and we have the sequential PLDs. Now, under each one of these, we have further categories. So under the combinational PLDs, what are some of the PLDs that you'll find here? The programmable read-only memory is actually considered as a programmable logic device. So that is one. Then we have the programmable logic array, as well as the programmable array logic. I don't know whether you covered this in third year. Can somebody confirm? Did you cover that in third year? Just unmute and say something. So under sequential PLDs, we have the simple PLDs, that is the SPLDs. And we also have the high capacity. We also have the high capacity PLDs, abbreviated as the HCPLDs. And of interest for us in this is the, sorry, for us here, we would be interested in these high capacity PLDs because that is where the FPGAs fall. So here we have the complex programmable logic devices, the CPLDs, and the FPGAs. So in this diagram, at least when we talk of the field programmable gate arrays, we can see where they fall under the within this digital ecosystem. So they are actually application specific ICs, but they are they fall under the PLDs, not the cell-based ASICs or the full custom ASICs. They fall under the PLDs. So meaning that you are not really starting your hardware design from scratch. You already have some basic fabric, a silicon fabric laid out for you, and your task really is to program that particular device, as opposed to a full custom ASIC where you are doing everything from scratch all the way to getting your chip into the fabs, the fabrication labs. But for us, for the FPGA, this is a chip that you actually buy off the shelf, and you can program it. And when we talk of programming, here we are referring to the hardware programming, not the processor kind of programming where you're dealing with software. So I hope this contextualizes what we'll be covering in our next in this session, and maybe in the next one session, the PLDs area, programmable logic devices, and we'll look at the combination of PLDs and the sequential PLDs, but our key interest will be on the FPGAs. So from this family diagram or tree, this family tree, something of that sort, we can see we have standard logic, ASICs, and microprocessors. So the difference, and quickly note that the difference between the micro computers or the microprocessors, the DSPs, between the DSPs and the other digital systems, and the other digital systems. When we talk of the other digital systems, we are referring to the standard logic and the ASICs, and that includes all the other subcategories within those systems, the standard logic and the ASICs. So the difference between this branch of digital systems and these other two branches of digital systems is that the former follow a programmed sequence of instructions. Sequence of instructions specified by the designer. And I think when you talk of by the designer, I believe as far as this area is concerned, you are all designers, because at one point I believe you must have programmed something. I think in second year or even in first year you had the maybe some programming sessions. So that already refers to you as the designer. So you have a sequence of instructions, and the CPU runs those instructions for you. But you will find that in other instances, or in many other instances, we get in new page, you'll find that in many instances or other instances, you will require faster uh, response than what a general purpose processor can offer you. So in many applications, will require a faster response than a micro computer or microprocessor or DSP architecture can offer or accommodate. And therefore, and in these cases, a conventional digital circuit must be used. And I think this is now more clear to us than before, especially with these the artificial intelligence. For those who one way or another may have interacted with those models, you would realize that if you were to train them on your local machines, it will be very slow, because of the heavy computational requirements that they have. And therefore, now we have digital circuits and devices kind of optimized for those kind of operations. So that means those devices were kind of custom made or tailored for those particular operations. And therefore, you'll find now that some of the selling points of some electronics, including some PCs, computers, and even mobile phones, they will claim that they are, is it AI enabled or something, or at least they can run some AI algorithms. That means that within their custom chips, whether it is the CPUs or they have some auxiliary accelerators for the AI inferencing and so forth, they have designed that particular chip or that particular area of the chip, for purposes of accelerating those kind of AI computations. So it's not just now the software level, but now at the hardware level, they have actually programmed that particular chip or the area of the chip specifically for those kind of the computations. And that is what we are saying here, that in these instances where the general purpose kind of CPUs are not able to offer the fast response required by some of these algorithms and models and so forth, then you will actually need to get a step further. Now you move from the software kind of programming to the hardware programming, where now you actually design a custom-made chip for that particular purpose. So so that means we are left with the standard logic and the ASIC, the ASIC, the standard logic and the ASICs to be able to 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 deliver or provide these kind of speeds that we may need. So with the standard logic, so standard logic devices, and when we talk of standard logic devices, you have interacted with them in the lab. We are talking of those basic, as examples, the basic logic gates, the AND gates, the OR gates. We also talking of the basic modules that are built from those kind of logic gates. These are the decoders, the multiplexers, and the rest. Yeah, so those standard logic devices sorry, the standard logic device chips will contain only simple gates. So they contain only simple gates. Or the medium scale integration level, the MSI type functions. So when we talk of the medium scale integration, maybe here we are looking at chips that have less than 100 gates, within them, less than 100 gates. So maybe some simple modules to perform simple functions. So the point here is that the standard logic devices cannot be suitable for most of these things that we are talking about. So hence, they are not suitable, hence not suitable for most of these conventional digital systems. So that means that for anything that requires greater speeds than can be offered by the microprocessors and the processors and so forth, we have already ruled out the standard logic devices. So we are left with the ASICs. So we are left with the ASICs, and that's really where higher speeds and speeds or the custom designs can be achieved. And that's the reason we will be looking at the lower level of the ASICs, or the lower level of ASIC design, because if we talk of the higher level, for example, these the cell-based and the full custom designs, it means now even the laying out of the transistors within the chip, that is the task of the designer to do. And not only doing that, but getting those designs all the way to the fab labs, for the actual manufacture of the chip, for you to achieve the full custom. So of course, we do not have the capacity to handle that, but at least the lower end of the ASICs, the PLDs, that is something that we can look at and have a feel of the what is hardware programming as opposed to just software programming. So that was more or less an introduction of why it is we are looking at PLDs and exactly where do PLDs fall within this digital ecosystem. And I hope that helps. So now we can get into the PLD proper, and from this we can see we have two categories: the combinational PLDs and the sequential PLDs. So those are the areas we'll be looking at as now we progress. So we can now comfortably what was the header for what we have covered here? Programmable logic devices. Well, we can now actually really get into the PLDs proper. So fundamentals. The fundamentals of programmable logic device circuitry. So the basic PLD will comprise. It will comprise of basic logic gates. These are the AND, the OR, and the NOT logic gates. And the functioning of a PLD is that it will implement or it implements a sum of products and this much of this is digital electronics covered, I believe, in that year. So when we talk of a sum of products, and these are what we refer to as the mini terms. How is a sum of products implemented using these basic gates? What do we need? Somebody just unmute and answer. What do we need to implement sum of products? Of course, we'll need the 3 gates anyway, because maybe one of the variables will need to be inverted, or its complement, and therefore in that case you'll need a NOT gate. And then for the sum of products you need both the AND and the OR gate. So here you find that mostly you are dealing with AND OR arrays. So the key elements of PLD circuitry is we have the input lines. We have the input lines. We have the input lines. We have the product lines, and we have our outputs, which are the sum of product outputs. So the input lines, these are the inputs. Inputs to the AND gate array, whereas the product lines are the outputs of those AND gate arrays, and our SOP, these are the outputs of our OR gate array. So a basic or a fundamental PLD circuit is as shown. So for purposes of time, I'd capture that elsewhere. So I'll just try to bring it I don't know whether I'll be able to capture it. Well, it doesn't seem to be possible to cover it, so I may need to bring it as an image, that is, because drawing it here will take quite some time. So, okay, this captures or shows a basic PLD circuitry. So, and here we are just showing a kind of a two input PLD, and how many outputs? Yeah, four. That is 2 to 4. So the idea here is that with variables A and B, you can be able to get any combination of those variables in our output, depending on how this is programmed. And we are calling this a programmable logic device. So how do you actually program this? So the key thing to note here, you can see our fuses. You recall when we were covering the read-only memories, there are those fusible links that we talked about. So these are the same fuses, and indeed, this is what will make this particular layout actually programmable. There is no other way you can change this, the functionality of this, apart from these fuses. So then we have the AND array. We have the AND gate arrays. We have our input lines. Input lines. Input lines. We also have product lines. And finally, we have the OR array, and of course, our sum of product. We have our sum of product outputs. So this is a basic PLD circuitry. And the key elements, as we can see, we have our input lines, which are inputs to the AND gates. Then we have the product lines, which are the outputs of our AND arrays. And then we have the sum of products, which are the outputs of our OR gate arrays. So I think this is very self-explanatory. We can see that each of the inputs A and B, they feed both an inverting buffer as well as an inverting buffer. In other words, a NOT gate, as it may be. And by doing so, we are able to produce the true and the inverted forms of each of these variables. So we are able to get A, the variable A in its true form, as one of the inputs of the AND gate. And we are also able to get the variable, the complement of that variable, the true form of variable A, that is the A complement, also as an input. And then each of these product lines is connected to the OR gates, the inputs of the OR gates, through fusible links. You know, we can see those fuses, and indeed those are the fuses that actually make these programmable. So by leaving them intact or by blowing them, then we are able to achieve some degree of hardware programming. So for example, if we want to have I don't know whether this space will be enough. Maybe I can put it here. If we want our output 1, that is O1, if we want our output O1 to give us A exclusive or B, we want our output 1, O1, to give us this combination. Which fuses do we need to have intact, and which ones do we need to have them blown for us to achieve this output? Anyone? So maybe to expand this a little bit. So when we talk of the fuses, we can regard these as fuse 1, 2, 3, and 4. We want that O1 to give us A exclusive or B. So fuses 1, 2, 3, 4. Which one do we retain? Which one do we keep? Somebody?
We'll have to have the fuse with the A prime B and the one with the A B prime. That's 2 and 3.
So we have an answer of 2 and 3. Yes. Any other response? Yes. So of course, this one we will kind of need to expand it so that we know the variable combinations that we need. So this is not A, B, or A and not B. So as such, what do we need? We need to keep the output. We need to make sure that the output, not A and B, that is product line 2, is connected to our OR gate, and also the A and not B, that is product line 3, is also connected to our OR gate. And as such, yes, we'll need to keep fuses 2 and 3 intact, right? So this means that we need to have fuses 2 and 3 at the OR gate O1 intact for us to achieve that. And what this means is that once that is done, we have actually programmed that particular device. I'm trying to get to a new page. Okay. And you can, whatever function you want to be at the output of any of these OR gates, you can program it as such by blowing or keeping intact the various fuses. So once all of the outputs, I know there is some background noise again, because once I connect back the charging, for some reason it seems to generate that noise. I don't know, probably it's the fan. So once we have programmed them in a similar manner, the device is said to be programmed, and as such, it will permanently generate the selected output function. So that is a very basic view of how the PLD works, or yeah, I think it tries to get the point across. But we have a simplified PLD symbology, and we'll see that the difference with what we have indicated here. You know, here we were showing even the fuses, you know, in those curvy lines and so forth. But there is a simpler way of communicating the same kind of circuitry. So we'll very quickly introduce that, the PLD symbology. And this really is a simplified representation of the internal circuitry. The PLD devices. So once again, I will get that simplified PLD symbology, and and bring it. Yes. Okay, okay. Thank you for that question. Just a few seconds. I put this up. Okay, yes. So, is that Linux? Yes. So we will I will respond to that question by taking us back to when we were dealing with the read-only memories. So we talked of the mask programmed ROMs, the MROM, which essentially were programmed at the manufacturer's point, and therefore once delivered, you can't change the functionality. Then a step further was the PROM, the programmable read-only memory. And if you are keen enough, we said that actually a PROM will be considered as a programmable logic device. Why? Because when we talked of the PROM, we saw this was a one-time programmable device. So one time, and that answers to your second question, that as far as these fuses are concerned, you cannot reverse. You cannot reverse that kind of programmability. But this, what we are looking at, is at the very basic ASIC stage, and also at the very basic PLD, because the PLD, they go all the way to FPGAs. As we shall see, the FPGAs, you are not really blowing the fuses in that scenario, and therefore you can change the functionality of the FPGA, as often as the case may be. So as far as the fuses are concerned, it is irreversible. So for the PROM, in our read-only memories, we said they were one-time programmable devices that you'd get the device with all these fuses, but you want to achieve a certain functionality. And to achieve that, there are some fuses you will leave intact, and there are other fuses you will have to blow. And once that is done, the device will permanently perform that functionality that you have incorporated by either leaving the fuses intact or blowing them. Now, the question was, how do you actually achieve that kind of programming? Uh, Honestly, I've not done anything that involves blowing of fuses, but I know, just like you are able to load some firmware into an MCU where you need a programmer to be able to upload that kind of code. There are also such programmers for blowing fuses for devices that need to have that as their way of programming. So at the very basic is you need a programmer for that particular kind of function of programming at the hardware level. So blowing some fuses and leaving others intact, there is programmers specific for that. So I think, but from a point of experience, I haven't really programmed anything that involves blowing of fuses. But for example, in the microcontroller world, I don't know, the current kind of MCUs, but you'll find, for example, when it comes to select, I don't know whether this is applicable to the Arduinos. I don't know, but at some point when I was dealing with the Atmel devices, that is the Atmega series of MCUs, they did allow you to actually blow or to program some fuses, which would now decide how you will be programming that particular chip, or yes, how you'll be programming that particular chip, because there were options of programming the chip. I can't remember the various protocols, but how you program the chip is determined by how some bootloader fuses are configured. So there was an option of configuring those bootloader fuses. And once that was done, I don't recall whether it was a one-time kind of thing, whether it was something reversible, but it was such a critical step that, from literature and from other experienced persons, you are advised not to interfere with those kind of bootloader fuses. You leave them as they are. So that was the closest I've really come as far as this blowing of fuses is concerned. But I believe you can get more information on the same. But as I've said, what we are discussing here is at the very basic, at the very basic level of the PLD. But when we get to the FPGAs, you realize that FPGA is a modern and complex device that really you are not blowing fuses and all that, but it still allows you to reconfigure your device at the hardware level as opposed to the software level. I hope that helps a bit, Lennox. Okay, so we can proceed with this. So this is a simplified version or representation of the internal circuitry of PLD. You'll have time to compare the two, but you can notice here, instead of now indicating the inverting and the non-inverting buffers, we can just indicate it as a single buffer with two outputs, one non-inverting and the other inverting. Then when it comes to indicating, these fuses and the various what can be programmed. Remember, in this case, we are able to program at the inputs of the OR gates, but the input lines are fixed. We cannot change where these input lines connect to. These ones are fixed, but we can program, or we can choose which product lines to appear in our output. So in this case, what is programmable really is the product lines, but you can indicate that in a more in a more concise manner by the use of dots and crosses. So here, when we have these dots, these are hardwired. They cannot be programmed. They are hardwired, meaning that our input lines are hardwired into the various AND gates. But on the output lines, we can indicate the programmability by either using crosses to indicate that we have an intact fuse there, or we leave it, those crossings with nothing. We don't introduce any crosses there. So that means there is no connection, or in other words, that is a blown fuse. So this is a more concise way of indicating the very same thing we have indicated up here. So for example, from this simplified representation, can somebody give me what is our output O1 from now this simplified? How do you interpret this? So there is intact fuse, there is blown fuse, and there is the hardwired part. What is our output O1? Somebody? Yes? Just unmute and speak. Did I lose you?
Not AB plus A, not B.
Who is that?
Mercy.
Okay, Mercy. Yeah, now, thank you, Mercy, for the attempt. But there is something you said that I didn't, I was not comfortable with. So output 1, you said it is not, you said not A?
Not AB
Uh-huh.
plus A, not B.
Okay, now that is where I was not comfortable with. You know, now we are in Boolean algebra. So this symbol here, it is commonly it is the addition symbol, but in this context we cannot say plus. Mercy, you can correct yourself. How do you
Or.
say that? Yes, you know, those are, it's a complete different meaning. So not A and B, or A and not B. So please don't say plus. If, at least at this level, just say or. Okay, so that is very correct. And maybe our output 2, O2, somebody else. What is our output 2?
AB.
AB. Who was that?
Ondere.
Okay, thank you. Okay, so I'm trying to, yeah, so I think that is very clear. So at least when you see this kind of symbology, you are able to interpret what it means. So maybe to very quickly capture a few notes about the same. So the input buffers, are represented as a single buffer with two outputs. That is, one is inverted and one is non-inverted. We also note that we are using a single line, that is in our input and also in the outputs. So in the inputs, we know for two input, or for two variable AND gate, we need two inputs. But we, for simplicity, we are showing that as a single line. So single line is used into the AND gate. Representing all the four inputs, or the four possible inputs. Remember, the inputs can be A, not A, B, not B. So we have four possible inputs, but we use a single line to represent those four inputs. So connections. Connections from the input variable lines to the AND gate, inputs are indicated as dots. That is, they are hardwired. Then another thing to note is that we have a single line into the OR gates. So in our previous diagram, we were showing all the four possible inputs to the OR gate independently, but here we are just using a single line. So a single line into the OR gates represents all the four product lines, and across represents an intact fuse. It represents an intact fuse connecting a product line to one input of the OR gate. So I think we can and okay, maybe the last note here is for all gate inputs, blown fuses, that is the unconnected. The blown fuses, that is the unconnected inputs, are assumed to be low, and for AND gate inputs, blown fuses are high. So somebody who is keen will be asking, how can we have blown fuses in the AND gate inputs, here, and we have not showed any fuses on this side. Everything is hardwired. So in the next phase of this session, we'll be looking at the different types of PLDs. Remember, we even under the PLDs we had combinational, and within combinational we had PROM, PLA, and PAL. So we'll see that the programmability is not just in the in the product lines, but we can also be able to program the input lines, and that is what actually gives rise to the different types of the combination of PLDs, the PROMs, the PAL, and the PLEs. So, but what we have showed here is just a symbol of one of those combination of PLDs, but it's very possible to have fuses in the add gate inputs, that is in our input lines, and that is what we are now getting into, the various types of combinational PLDs. Can somebody give us one example of a combinational PLD? One example? Somebody? Now this is the tragedy of these classes. Joseph Paul, are you with us?
Yes.
Yes. Can you help us? Should I repeat the question? Joseph Paul?
No, I had the question. The combinational PLDs.
What have they done?
An example. You said you wanted an example.
Yes, kindly.
There is PROM. And
Okay, the class rep has come to your rescue. So we have the PROM as an example of a combination of PLD, and that is what we'll very quickly talk about, very quickly. So we already, from our previous sessions, we already know that PROM is programmable. It is it's programmable. So when we covered it, we covered it from a memory device angle, that PROM, we could use it to store a 0 or a 1, as a memory device. But you will also recall that in the use cases of read-only memories, we gave an example where we can have a ROM device store some mathematical functions, where we did an example, I think it was x squared plus something. And in that case, we saw that we can actually use a read-only memory to store some functions, so that permanently we'll be getting outputs of a particular function. And in essence, that's really the PLD, the ROM, the PROM aspect as a PLD, that we can actually store some functions, not just zeros and ones, as far as memory is concerned, but also some functions that we are able to permanently execute because they are already programmed and hardwired now into the device by blowing or leaving certain fuses intact. So that is the context in which we are looking at the PROM now as a programmable logic device. So yes, it can be a memory device. But even from the example that we saw, one of the use cases, it can actually be a programmable logic device. It can store some functions. So by calling it a PLD, a programmable logic device, it's just a way of using a PROM it's just a way of using a PROM and thinking of it and thinking of its purpose as implementing the sum of product logic expressions rather than just storing values in memory locations, rather than just storing values in memory locations. So we saw it, we can implement mathematical functions. We are now saying we can implement some logic expressions and so forth. So from our fundamental PLD circuitry, we have seen that the key elements. We have the input lines, which are feeding into the AND gates. We have the output lines, the output of those AND gates feeding into the OR gate arrays. And then we have the outputs of our OR gate arrays, which now form our outputs. And we have said the inputs can be programmable, so we can have fuses in the input lines. We can also have fuses in the output, in the product lines, that is the inputs to the OR gates. And so far, in our example here, we have been looking at cases where we have fuses in the product lines. Yeah, fuses in the product lines. But these fuses can also be in the input lines. So for PROM, this is essentially a PROM. What we are showing here is essentially a programmable read-only memory, in the sense that we have fuses only in the product lines. So for PROM, we will note that we have a fixed AND array. We have a fixed AND array, so it is hardwired, it's not programmable. And this is generally a decoder. And if you recall our sessions, the raw memory matrix, we had those memory cells, the transistors, and then we had the decoder coming in to select the various memory locations. So that decoder, in this case, is what we are looking at it as the fixed AND array. But now our OR array, that is our product lines, are programmable. So we have a programmable OR array. So that is the structure of a PROM. The structure of a PROM. So we have inputs coming in, and as obtaining our outputs. These are our inputs. These are our outputs. So just as the diagram shows, is that for PROM, the array is fixed. That is not programmable. It's not programmable, and is implemented as a decoder. The OR gate array, the OR array is programmable. Is programmable. So if you look, so based on this kind of configuration, and we have seen what we have here is essentially a PROM, we see that all our possible inputs are actually hardwired. We have no way of selecting our inputs. All those inputs are will be available. And remember, here we are just showing two inputs, A and B. Those variables can be many. We can be having 20 or whatever the case may be. So in that case, we note that a PROM, now we are looking at it as a PLD. PROM is suitable. PROM is suitable for those applications where every possible input combination is required. To generate the output functions. For example, in data storage, that is essentially what we just looked at last time, lookup tables. So that is where they are suitable. However, when implementing sum of product expressions, PROMs are not very efficient. They don't make very efficient use of circuitry. Even before I give the reason, can somebody tell us, from what we have said about PROM, when we are implementing a sum of product expression, why would we say that a PROM does not make efficient use of the circuitry? Yes?
Okay, you have all those connections connected to the OR array.
That was fast. Who is this? I didn't really hear you well.
I'm saying you have all the connections connected to the OR array that will not be used.
Okay. Yes. Who is that?
Ngesa?
Name? Okay. Okay. Thank you. Yes. 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 So that is correct. We have all the possible combinations of the inputs actually wired, because we are not able to, or we cannot really choose which inputs we want and which inputs are not necessarily in that particular expression. So whether you need the variable a or b or c in your expression, and maybe D is not, doesn't feature anywhere in your logic expression, but it's still hardwired in your circuitry. So that is the reason behind this. So we can see that each, they don't make efficient use of the circuitry, because each combination of the address inputs must be fully decoded, and each expanded product term has an associated fuse that is used to OR them together. And of course, those are the fuses that you either blow or leave intact to OR them together. And that is inefficient because SOP expressions may not need all those product terms. So SOP expressions may not require all the product terms and fuses. So I think that is very clear. We don't need to spend much time there. So when we're not looking at the PROM any deeper than that, as far as it was concerned in the ROM, we have an idea of, at the the matrix level, how it looks and so forth, including this we are seeing the decoder. So, and the fuses. So the next example of a combinational PLD is the programmable array logic. The programmable array logic, that is the PAL. And in this case, we find that now our fuses are not in the product lines, but they are on the input lines. So in this case, we have the AND array being the one that is programmable. So we have a programmable AND array, and then our OR array is now fixed. So we have fixed, we have fixed. Sorry for the background noise if it's back. So we have the fixed OR array, of our inputs and outputs. We can make a few notes on this. Now this we have said for the PROM doesn't make efficient use of the circuitry, but now this programmable array logic, because now we can decide which inputs really do we need, you know, so we can program the input side. So this makes a better or efficient use of circuitry. For sum of product expressions compared to the PROM. So it has a similar and or structure to that of the PROM, but now the AND array is programmable and the OR array is fixed. So that is clear in the diagram. We don't need to write that. Another point that we can note about this is that in Perl, that is the programmable array logic, every AND gate now can be programmed, and you know, and now the programming we're talking about here is just tied to blowing of fuses, you know, not writing some software. So it can be programmed to generate any desired product of the n input variables. And their complements. So that is sufficient. So let me see whether I have a circuitry of a PAL. Yeah, so yes, there is one, and actually I will put it here. So the PROM we indicated it's fixed and array and programmable or array, and then okay, I think I will put those diagrams at the end of the third one. So let us look at the programmable logic array. I'm not very sure about all these namings, the programmable array logic, and then we have programmable logic array. I really don't know how these devices were named, but that is how they are referred to. So we can't refer them otherwise. So we have PAL and we have PLA. And now for programmable logic array, the input lines and the output lines and the product lines are actually programmable. So we have both AND array being programmable as well as the OR array being programmable. So we have programmable and array, and we have programmable. We have programmable or array. So even before we make any notes on this, comparing the three. So we had the PROM, the AND array is fixed, the OR array is programmable. Then we have the PAL, the AND array is programmable, the fixed array is the OR array is fixed, and then PLA, we have both the AND and the OR arrays being programmable. Out of the three, which one gives the designer more flexibility? Out of the three, somebody?
Programmable logic array. Really?
Is who is that? Who is that?
Eric. Well,
Eric. Eric who?
Gola.
Ogola. Okay. Thank you. Yes, that is correct. That and of course it is self-evident that if you can be able to program both the AND and the OR arrays, then it gives more flexibility. So both the AND and we can note that. Both the and OR arrays are programmable. They are programmable, and it is the most flexible because of that reason. It is the most flexible, and its application is that it is used mostly in state machine design, where a large number of product terms are needed in each sub expression. You know, the takeaway point here is that the PLE is the most flexible because it allows programmability of those two arrays. So at this point, I can bring in the diagrams where we talked of when we first get the PROM as PLD, where we said that the just to even as I bring that up here, we said that PROM, what is programmable and what is fixed in PROM? Charles Essinien or Essinien, are you with us?
Yes, I'm in class.
Yes, kindly, can you help us there?
In the theorem, we said the AND array is fixed, and the OR array is programmable.
Okay, yes, thank you, and that is correct. And I'm glad that you're actually listening in because I don't know, maybe you are a very good class, but I have a feeling that a large number might be up to something else, probably still academics, but maybe not 502. So let me just paste that one here. I will be sharing these notes with you, so that's why I'm trying to make sure all the information that you may need is captured here. So this is the PROM as a PLD, and this speaks to the fixed AND array and the programmable OR array. So you can see all the fuses are present here, and you can blow or leave them in fixed as the case may be. Okay, so and as well as expand this because the other one cannot fit there. So the next one is the PAL. So let me see who we have in class. We have Moses Gray. Can you help us there?
Is it still the question about the theorem?
You tell us. I'm not sure whether that's still the question. You just answered the question that you last had.
Well, the last question you asked Charles about the theorem, and he said that the AND array is fixed while the OR is programmable.
Okay, thank you. At least you have also been in class, maybe until the last 2 minutes. Your mind might have wandered a little bit. Let's hear from. But thank you. That is correct as far as the PROM is concerned. Rebecca Kerubu. You'd rather say something than keeping quiet. Yes, Rebecca? Okay. Stephen Wanyondu, you're with us? Yes, Stephen, I cannot hear you.
I said I'm with you.
Sorry, you're still here?
Yeah.
So can you maybe assist us with that query?
I think for a moment you're inaudible. I think I will also answer the same as Dre.
Okay. Then finally, before we progress, maybe we can hear from who? From Kipkosgei Bredan. Kipkosgei, are you with us? I think Kipkosgei might have stepped out a bit. So anyway, who can help us with that question?
For the programmable array logic, we have the AND array being programmable and the OR array being fixed.
Okay. Yes. Thank you, Samuel. That is the answer that I was looking for. So it is unfortunate that I was inaudible to some students for some time, but I hope you'll be able to catch up. So yes, so the PAL, I was actually looking for that diagram so that I can bring it there. So for the PAL, AND array is programmable, the OR array is fixed. Now, I'm not sure how I'll be able to transfer this. Okay. So please, we are almost coming to an end of our 2-hour session. Just be a little bit patient. Yeah, so this is our programmable array logic, where now we are depicting our AND array as programmable and our OR array as fixed. And of course, when you come to the PLA, I will not need to put it here. We can now imagine that now we have all these crosses even on this other side of the OR array the side. So we have covered the combinational PLDs, and now our next part will be the sequential PLDs. So just to get back to our family tree, the PLDs, we have covered the combination of PLDs, PROM, PLA, PAL, and as I said, these are really at the lower end, the basic kind of the PLDs, where programming really is about the fuses and so forth. And now we will be looking at the sequential PLDs, and this is where the FPGAs come in, and we'll spend some time focusing on the FPGAs because those are things that are you are more likely to interact with in the market, and they have their own use cases, which with time you may find to be very much applicable for you, in your practice, especially in the area of embedded systems. So we'll spend some time on the FPGAs when we are looking at the sequential PLDs. So I will not start really on that new subtopic of sequential PLDs now. Let us do that in our next online session, because as I said, and as you can see, if I was to come in class and kind of draw some of this, it will take all our time. But now even for the FPGAs, we'll do some hardware programming that is using some hardware languages, the hardware description languages, and that will call for some kind of demonstration. So the online will be most suitable for that. So I think that is sufficient for today. I will share these notes, and as I said, next week, unfortunately, I will be attending some conference Monday to Wednesday, and therefore our Monday class will not be possible. But I do believe we can have